Good afternoon, dear ladies and gentlemen, dear colleagues, dear Lana, dear Kavi. It is a great pleasure to introduce two young colleagues today who will give their inaugural lectures. We will do these two lectures back to back, and I will give the introduction just before each presentation. And the first colleague who I have the pleasure and honor of introducing is Lana Josipovic. So Lana joined our department, the ITED, in January 2022 as tenure-track assistant professor of digital systems and design automation. She became a member of the Computer Engineering and Networks Laboratory, or the German acronym TIC. And her background, I really must say, fits our department perfectly, because she is by training an electrical engineer. She got a BSc and her MSc from the University of Zagreb in Croatia. She then moved to Switzerland and obtained a PhD degree in computer science from EPFL in 2021. Her research interests concern reconfigurable computing and electronic design automation, with an emphasis on high-level synthesis techniques to generate efficient digital circuits from software programs. And despite of her young age, she already has achieved many accomplishments, of which I will just list the most important ones. So, for example, on the science side, she has developed Dynamatic, an open source compiler that produces dynamically scheduled circuits from C and C++ code. And she has received a long list of awards. And I'll just mention a few here. So, for example, she got the Outstanding Dissertation Award from the European Design and Automation Association and from EPFL. She got the Fritz Kotter Award, the Google PhD Fellowship in Systems and Networking, the Best Paper Award at FPGA 2020, and earlier in her career in 2015, she was elected by Google as a Women Techmakers Scholarship for Community and Diversity Engagement. So Lana, welcome to the ITED, welcome to ETH. It is great to have you here. We very much look forward to your presentation, and we look forward even more to having you in our department for many, many years to come. Thank you for joining us.
Thanks, Klaas, for the very nice introduction. And hi, everyone. Thank you for joining today. I'm very excited to talk to you about some of the recent trends and challenges in generating efficient digital circuits from high-level software programs. Now, as you all know, our computational demands are continuously increasing. General-purpose processors, CPUs, are not always able to keep up with these trends. And this is why hardware acceleration is becoming increasingly important. People are using different types of hardware accelerators, from FPGAs to ASICs, and employing them for very different applications, from Microsoft using FPGAs in data centers, Google building dedicated chips for machine learning, and so on, all pointing to the importance of this paradigm in the years to come, because it promises to give us high parallelism and very good energy efficiency. And actually, we see the similar trends on the market. Many big processor companies are recently acquiring main FPGA companies such as Altera and Xilinx, also pointing to the fact that all these processor vendors see the need in extending their portfolio with something like FPGA's reconfigurable chips. But there is a problem with this way of doing computing. Doing hardware design is very difficult. One needs to use a very low-level programming model. Maybe some of you suffered with VHDL or Verilog or something of this sort at some point of your life. It is something that hardware designers can do, but other people not really. But we are now entering an era where all these very different users, from machine learning experts, physicists, and CERN even, need to benefit from this paradigm. And this is why we need high-level synthesis, or HLS. HLS tools generate digital circuits, hardware designs, automatically from high-level software code, C, C++, or anything of the sort. And the idea is to enable not only hardware, but also software developers to benefit from hardware design, and in general to increase hardware design efficiency, to be able to do it in a faster and easier way. And this is great. HLS tools have gained some popularity recently, but still, we are not there yet. There are many problems in really benefiting from this concept and enabling different users to benefit from hardware acceleration. Now let's take a look at some of these challenges, starting from the more software-oriented ones to the more hardware-related problems. First of all, although we want HLS to be accessible to everyone, it is still not really meant for people who do not have hardware design expertise. To get good results out of these automated flows, one still needs to tune and refactor the code in particular ways that the tool will then understand and give us a good quality circuit out. To illustrate, this is a very small example of a for loop where we are just reading some values, adding them up and storing back into memory. If we just throw this code to the HLS tool as it is, the execution time will not be that great. But if I rewrite it like we see here below, then actually we go from 300,000 or 30,000 clock cycles to only 300 clock cycles because we help the HLS tool to give us a good quality design. We add different annotations to specify parallelism, tell it how to organize the memory interface. This is all great, but it defeats a lot of the purpose of doing HLS because now I need to be a hardware designer to do this well, and again, it takes me time to find this good configuration. Secondly, although HLS compilers work very well in particular cases, they often fail in giving us good parallelism in different types of software code that we see today. To use an example, something that many people here use, a sparse matrix vector multiplication, it seems like a very simple piece of code, and ideally we should be able to get a good accelerator out. But it turns out that there are many features of this code which are not really understandable by standard HLS tools, all these variabilities, irregular behaviors that prevent them from producing good quality, high throughput pipelines. And we will talk about this problem more in a bit. Next, HLS circuits and hardware design in general relies heavily on functional verification at the hardware level. What this means, again, for the people who maybe did some hardware design, probably you spent a lot of time staring at waveforms like this one, where one needs to really look at all of the signal values, figure out whether they are in 0 or in 1 in a particular point of time. It takes forever to do, and of course the amount of testing that we can actually do is limited, which prevents the usage of this in critical applications or when we are targeting hardware that may be expensive, like for instance ASICs. And this is one of the reasons why HLS today typically targets reconfigurable platforms or FPGAs. They are great because they are these flexible platforms, like the one that we see here, with logic blocks that we can reconfigure to do different tasks. We like this flexibility because we can change the task that is running on our chip. But of course, this generality leads to performance and power inefficiencies. What is more, it is very difficult at these higher levels of the HLS flow to account for what happens on the actual hardware, and this causes us even more problems. So all of these challenges need to be resolved if we actually want to benefit from high-level synthesis and consequently from hardware acceleration. Let me go deeper into one of these problems that we have been trying to overcome in the past years: how to extract more parallelism from software code in the high-level synthesis process. So let's take a quick look at how standard HLS works. It takes some piece of code, for instance, the for loop that we have here. It automatically produces a data path of operations that implement this functionality. There are some loads that correspond to the reads here, a multiplication, an addition, and so on. And on the side, there is this static controller, which essentially dictates when each of these operations needs to trigger. It implements what we call an operation schedule. What is important to note here is that this schedule, that dictates when things are going to happen, is devised at compile time, while looking at the code, and before the circuit actually executes. You can think of this as the type of scheduling that we normally see, for instance, in trains or in trams. One defines where the train will go beforehand, we define all the stops, how long we need to stop at each point, everything is set before the train actually leaves on the journey. And this is exactly what we have in HLS today. So let's do the job of this HLS tool, and let's create a schedule for the data path that we have on the left. Our job here is to place operations into clock cycles, this is the time units that we care about here, as soon as we can actually execute them. So we can start with the loads. Both of the loads can happen in the first clock cycle. After the loads, we can do the multiplication. It needs to wait for the loads to finish because it uses the data of these loads. Then we can do an addition, and then we can repeat this as many times as we have loop iterations. Perfectly fine, but of course it doesn't give us the performance that we want. We are essentially doing everything sequentially, one after the other. The data path is not really used in the best possible way. So what typically HLS tools try to do, they try to squeeze these iterations together as much as possible to get us high throughput and good performance. In this case, we are starting a new loop iteration on every clock cycle, and this is exactly where we want it to be. Notice that it now takes only 6 clock cycles to execute versus 12 in the previous case. And this is great when standard HLS has all the information to devise such a schedule like the one we have below. But there are many cases where it fails in doing this, and the schedule that we get is not really what we would like. Let's take a look at one such example. It is a very simple histogram kernel where we are reading a value of x, using it to address array hist, performing some computation, and then storing back into hist. Now here, depending on the values of x, there may or may not be read after write dependencies between some loop iterations. In my example here, there is this load hist of 4 that targets the same memory address as the previous store. So of course the load needs to happen after the previous store completes, otherwise we are reading the wrong value from memory. So what does an HLS tool do? It looks at this code, it needs to create a schedule. At this point, it has no idea what the values of x are because they have not yet been read from memory. So it has no choice but to create a schedule like the one that we see below, where every load of hist is scheduled for after the previous store completes. This is perfectly correct for any value of x. If there is any dependency, for sure the load is happening after and there is no problem at all. But just like in our previous case, this is not the level of parallelism that we would want to have. Maybe all values of x are different, there is never a dependency, and I'm always waiting for no reason at all. So what we would like to achieve is something like the schedule below, where those iterations that are independent are overlapped perfectly, and the load is postponed for after the store only when this is actually required. And the idea to achieving this behavior is to refrain from triggering operations through this pre-planned static controller that dictates when things are going to happen and is designed at compile time before we have all the critical information. And to create circuits that have a distributed control mechanism where different components communicate with a set of handshake signals and decide dynamically at runtime when to exchange pieces of data among them. When I compute my thing, if my successor is ready to take it, I will simply hand over my data. This gives us the flexibility to adapt the schedule at runtime to particular memory data control outcomes. Or in terms of our analogy from before, we do not want this type of scheduling that we have in trains, where someone devises the schedule beforehand. In this case, you need to stop on every stop, even though no one may be entering or exiting our train. What we want is the flexibility of taking a car. I want to be able to drive slower or drive faster, change the route as I go, stop if I actually need to stop, but only then. This is the type of behavior that we would like our circuits to achieve. So in the recent years, we developed a complete strategy to create such dynamically scheduled, we also call them data flow circuits, from high-level software code. First, there was a bunch of things that we needed to do to catch up with standard existing techniques. We want to be able to pipeline for high performance and minimize the area of our circuit by sharing functional units among different operations. And next, we want to actually benefit from the dynamic properties that our circuits have to offer by implementing memory interfaces that support out-of-order execution and exploring new features such as speculation, executing some operations that may or may not be correct. So I'll just give you a flavor of some of these problems. Let's go back to our histogram example from before. The code is the same as the one that we have seen. And on the left, there is the data flow circuit that implements this functionality. From now on, I will not show explicitly the data and these handshake signals, but remember that they are always there. So whenever there is an edge connecting two components, it represents the bundle of all of this information. If we take a look inside, the operations of our code are translated directly into the corresponding data flow operators. And then the for loop itself is implemented with a merge and a branch node. A merge here receives data from the starting point to start the execution, or it takes the updated value as it comes from the branch. And the branch is the one that decides when to exit the program. It compares the iterator with n and then either decides to send it to the exit or it sends it back into the loop. We're going to use registers or buffers like any standard synchronous design, and then forks to replicate data to send it to multiple successors. So how does this work? A data will enter through the starting point of the program into the buffer, and from here it will be sent to all of the successors, including this branch, that will then send the data back into the loop. Notice now that we have this data, we also call them tokens, that circulates from the merge to the branch and back. And we want this to happen as quickly as possible because we want our circuits to have high throughput and to process data with a high rate. But we cannot do a very good job at this point because there are some operations like our adder here that are not able to take data that is arriving from the predecessors. In this case, the adder needs both of its operands to execute. Only one of them is available, so it cannot be consumed yet. There is a stall propagating through this path all the way to the next piece of data that is coming. Same thing here with the store. The store needs the address and the data to actually trigger. The address is there, the data is not there yet, so the address needs to be stalled. And this prevents our new pieces of data from quickly moving forward. And this is a problem for our performance because this back pressure from the slow paths prevents us from extracting any parallelism at all. There is no pipelining, and the schedule that we get is essentially the same that we had with the standard HLS techniques that we wanted to avoid. So there is clearly something that we need to do to be able to pipeline our circuits for high performance. And the idea is the following. In addition to these registers or buffers that now hold pieces of data in only some places, let me add larger buffers or FIFOs in particular places to regulate the throughput of my system. This is the situation from before. There were these stalls that were preventing data from moving forward. And now that we have these FIFOs, they will always be able to consume data as it arrives. There will be no stall on the data that comes next, and our data will move quickly through our circuits, giving us high performance. The challenge here, of course, is how to decide where to put these FIFOs and how big they need to be. And for this purpose, we developed a complete mathematical modeling techniques that essentially analyzes how the data moves through and determines how to place and size these buffers. What is interesting is that this is connected to the problem of deciding how many functional units to employ. We can use the exact same notion to analyze which units are underutilized, computing things at a low rate, and then decide to implement their functionality on a single shared unit instead. So we reduce the size of our circuit without hurting our performance at all. So this is where we were. There was this back pressure that was preventing us from pipelining our design. Now we know how to actually achieve a high throughput pipeline because of these buffers that we have placed. We can start a new loop iteration on every consecutive clock cycle. Exactly what we wanted, except there is something that we forgot, and this is the read after write dependencies. Remember my example from before? There were some of these situations where a load targets the same address as a previous store. Nothing in my circuit so far prevents us from making a mistake. In fact, in this case, the load actually runs ahead before the previous store, which of course means we are reading the wrong value. And this brings us to our second group of problems, how to dynamically resolve all of these memory conflicts and ensure that we are never making a mistake when reading or writing into memory. So let's go back to the same example, now with the memory interface shown. What we actually need is a mechanism that we know from the processor world, which is a load store queue, a dedicated structure that receives memory accesses out of order, but then ensures that all those that have any sort of dependence are actually reordered before sending them to memory. So in our case, if I get multiple loads from different iterations before any of the stores, it is no longer a problem because now the load store queue knows, because it keeps them inside on an appropriate order, it knows that this load of hist can move forward only if it targets a different address than the previous store. Otherwise, it needs to wait for the store to complete. And with this, we finally get the pipeline that we wanted. We move ahead quickly when there are no conflicts between the iterations because of the buffering that we developed. And now we know how to handle dependencies as well because of this load store queue that helps us to figure out dynamically where they are and stalls the pipeline only when this is actually needed. This is a type of behavior that standard high-level synthesis would not be able to achieve because it doesn't have this flexibility to adapt the pipeline at runtime to these particular situations. So this is one new thing that we introduced, and actually there is another mechanism that we know from the processor world, which we are now able to support as well, which is speculative execution. We want to execute some operations before we know that they're actually correct or required. They're going to travel through our data flow network and execute operations quickly. We will then have a mechanism that ensures that in case we misspeculated, we did the wrong thing, we can actually kill the data that we computed something wrong with and replay the computation later with the correct values. Again, something that standard HLS could not support because it does not have the flexibility to squash and replay and change its execution. So all of these features are implemented in Dynamatic, our open source HLS compiler that takes C, C++ code and produces dynamically scheduled circuits that support all of these behaviors. We have shown on different benchmarks that we can achieve significant speedups by exploiting these new capabilities that standard HLS could not. So this is where we stopped with our challenges. We tried to explore ways to extract more parallelism from software code by introducing new features and behaviors to our HLS flow. This is great, we made some progress, but we are still not done with this challenge and certainly not with the other ones that we have. So what we did so far is extract so-called instruction-level parallelism from the software code that we have, typically some C or C++. So our circuits essentially represent this single sequential software thread where the data moves forward, for instance, from one loop into another. And what we can now do well is move this data quickly through these loops. But remember that we are in a spatial hardware accelerators where we have a lot of resources available, and actually we want to do many of these things in parallel as well to gain even better performance. So in terms of C-based synthesis, we have made some progress in exploiting this spatial parallelism as well, for instance, by restructuring the circuit in particular ways to let multiple loops and multiple pieces of code execute in parallel. But there is only so much that we can do starting from this fundamentally sequential code representation. So a long-standing question in HLS is what is the programming model, the way people express their application to the tool that we should be using. We need something that allows the user to conveniently express their application, but also allows the HLS tool to exploit all of these different parallelism dimensions and really use the hardware that we have in the best possible way. Remember, we mentioned the problem of functional verification. It is time-consuming, but also has quite limited capabilities. This is also something that we need to resolve if we really want to bring hardware design to software developers. So a hope to remove some of this difficulty is to use different forms of formal verification to prove the correctness of the HLS compilation process and to verify the circuits that come out in a complete way. A nice thing that we can do is also use these formal methods to improve the circuits that we get from these tools in the ways that we were not able to do before. This is something that we are exploring right now. The idea is to prove the absence of particular behavioral scenarios in our data flow designs produced through HLS. If we prove that some things will certainly never happen, we can actually remove a lot of this generic logic that our circuits contain and replace it with much simpler, cheaper structures that actually support all of the behaviors that our circuit will ever exhibit. So this usage of formal methods is something that can significantly improve the circuits that we get and the HLS flows in general. Finally, we talked before about the inefficiencies of using reconfigurable FPGAs. It is certainly a big problem because we suffer a lot when our circuits actually get implemented on the reconfigurable platform. So there are two ways to go about it. From the HLS side, we should be thinking about different FPGA-oriented optimizations and transformations that helps us to understand what will happen later in the FPGA flow and how to optimize our hardware in the best possible way to fit on the platform that we have. We started exploring this in terms of achieving accurate frequency, but of course, there are many other dimensions that one can explore. In the longer term, it is of course a question whether we should be using classic FPGAs at all. Perhaps this bit level generality that we have is a bit too much for the types of applications that we have and not really compatible with the software code that we are trying to accelerate. There could be something much better suited to map high-level programs, for instance, some word-oriented architectures and something that has predefined blocks at a different level of granularity. So all of these are challenges and questions that we are exploring in the Digital Systems and Design Automation group. Our goal is to bridge this still existing gap between software and hardware and to really enable different users to benefit from hardware acceleration. For this purpose, we are interested in looking into different programming models to program the hardware from a software high-level description, new compilation techniques that help us to do a good job and extract as much parallelism from the high-level code that we get, and finally, how to actually build these hardware accelerators to make them work well for the applications that we need. Solving all of this problem will hopefully enable really different users to benefit from hardware acceleration in different compute-intensive applications. Of course, none of this would be possible without the other group members. We are a new and still quite small group with 2 PhD students, Carmina and Jacqui, who already made really great advancements in tackling all the challenges that we just talked about. And I very much look forward to working with them on many fun problems in the coming years. Thank you all for your attention and look forward to chatting with you at the apéro later.